today we will discuss some properties of Bessel functions. We have already seen that Bessel functions are solutions of Bessel differential equation, and we particularly looked at those functions for integer values of v, okay, the parameter that appears in the Bessel equation. So these Bessel functions, okay, so if you remember, we defined jv of x in the following form as x raised to v sum over n equal to 0 to infinity, then you had minus 1 raised to n x raised to 2n divided by 2 raised to 2n plus v n factorial n plus v factorial. Okay, so this was how the Bessel functions were defined for integer v. Okay, and what is important in this, okay, you can write this in a slightly different form, x by 2 raised to v sum over n equal to 0 to infinity, and I will write this as minus 1 raised to n, and then I will write x by 2 raised to 2n times 1 over n factorial n plus v factorial. Okay. Now, what is important to note about these Bessel functions is that it is an infinite series, it goes from 0 to infinity, it is not a polynomial. Okay. So, Bessel function is an infinite series, but it is a convergent series, okay, it converges. Okay. So, for example, if you look at v equal to 0, so j 0 of x, this is the infinite series for v equal to 0. Okay. So, when v equal to 0, the x raised to v term will drop out. Okay. So, what you will be left with is sum over n equal to 0 to infinity minus 1 raised to n x raised to 2n divided by 2 raised to 2n n factorial n factorial. Okay. So we see n factorial square 2 raised to n square. So I can write this in this form, sum over n equal to 0 to infinity minus 1 raised to n, and then I have x raised to n divided by 2 raised to n n factorial, the whole thing square. Okay. So it's not obvious what this is, okay, but this is a convergent series, and this is the expression for j0. Okay. Similarly, you can write for j1 and so on. Okay. Now, I will just illustrate what these Bessel functions look like. So suppose this is clearly a function of x, okay, and since it involves only even powers of x, it is an even function of x. If I plot j of x as a function of x, so if I plot j0 of x as a function of x, okay, then clearly I will use the red color. So when x equal to 0, when x is equal to 0, okay, then this becomes basically 1. So x raised to 2n, okay, that is equal to 0. So when x equal to 0, okay, so you just get you do not have clearly the only term that contributes is the n equal to 0 term, okay, and the n equal to 0 term, okay, if you put n equal to 0 here, so this will become 1, okay, here you have 1, here you have 2 raised to 0, which is 1 factorial 1 factorial. So when x equal to 0, okay, then this goes to 1, and the behavior of this as x changes, okay, so it looks, I'll just show what the behavior looks like. Okay, so it looks something like this, and it is symmetric about the axis. So it looks like this. Okay, so it has oscillations like sines and cosines, so it keeps oscillating in this way. Okay, and if you look at j1 of x, okay, now j1 of x, okay, it will look slightly different. I will just this is, so if I also want to show j1 of x, okay, on the same graph. So this is my j0, Now, if I want to show j1 of x, I will use a different color, and in this case if you look at j1 of x, okay, now in that case what you have is you have a slightly different function, okay, and in this case you have x raised to 1, leading term of x raised to 1, okay. So this goes to 0 when x equal to 0, and it has a slightly different functional form. I will just draw this, but it is also oscillating. It also shows similar oscillations, and this is actually odd function, okay. So because of this leading x raised to 1 in front of it, it is an odd function. So it looks like this, okay. So this is x raised to 1, okay. So this is j1 of x. So the point is all the even v's correspond to even functions, odd v's correspond to odd functions, okay. And remember, it is an infinite series. I cannot write this in a closed form, okay. I cannot write any of these in a closed form. All right. Now there are some more interesting properties of this Bessel function. So this jv of x, which has this long expression, okay, I'll just mention some of these. You don't have to remember any of these, okay, but these are just for your information. So I can write jv of x in an integral form, okay. I can write this in the following integral form. I can write it as 1 over pi integral 0 to pi cosine of vy minus x sine y dy. So I am taking a cosine of a quantity that has x sine y, okay. So you are integrating over y. So this is a function of x. So this is one way to express it. Alternatively, you can write it as in a slightly different way, 1 over 2 pi integral minus pi to pi. So this cosine can be expressed in terms of exponentials, and you can show that this is equal to e to the I, and you have exactly the same thing, vy minus x sine y dy. So I can write this in this form. So these integral expressions actually showing that this integral gives you the same as this series is a bit of an exercise. You have to work it out. You have to do a Taylor expansion and then do the integral, okay. But I won't bother that. I'll just mention that this is one of the integral expressions, okay. So these expressions I don't expect you to remember, okay, but these are good things to know, okay. And in fact Bessel had originally used some of these expansions to derive some properties of the Bessel functions, okay. Now what are the other interesting things about Bessel functions, okay. So the other interesting thing is that suppose I take d by dx of x raised to v times jv of x. So I take the derivative with respect to x of this whole thing, I get x raised to v jv minus 1 of x, okay. On the other hand, if I take a derivative of x raised to minus v jv of x, then I get minus x raised to minus v jv plus 1 of x, okay. So these are again interesting properties regarding derivatives of x raised to v times a Bessel function, okay. Using these two, you can derive a recursion relation for Bessel functions, okay. And I will just write the recursion relations, and again I do not expect you to remember these, but these are useful things for you to know. So you can write two recursion relations. You can write jv plus 1 of x plus jv minus 1 of x equal to 2v by x divided by x jv of x, and the other recursion relation that can be written is jv minus 1 of x minus j of v plus 1 of x. This is twice jv prime of x, okay. So these are some of the relations that you can write, Okay. Now again as I said, I do not expect you to remember the relations for Bessel functions, but the fact that you have these recursion relations is again very interesting. And notice that again once again j of v couples to j of v plus 1 and v minus 1. Okay, and this turned out to be fairly useful in say the Hermite equation, okay, which we used to analyze the quantum harmonic oscillator. Okay. Some other properties. Okay. So, if v is a half integer. Okay. So, for example, j of half of x, okay, you can work it out, and this turns out to have a fairly nice expression. So, it turns out to be square root of 2 by pi x. Okay, the square root of 2 by pi is a constant that is added, but you have basically 1 by root x times sine x. So, it has a very simple connection with sine x. So, it is just sine x divided by square root of x. Similarly, j of minus half of x, okay, and you can imagine what this will be. This is just 2 by pi x cosine of x. Okay. And in fact using this j of half and j of minus half, you can derive j of 3 halves, j of 5 halves, j of minus 3 half, and all the other half integer Bessel functions. Okay. So, basically the point is that half integer Bessel functions are related to sines and cosines. Okay. So, this is one useful thing to remember. Okay. The other thing is that zeros of Bessel function. Okay, so these have significance. Okay, I'll just mention that they have significance, and we'll see in a minute where they in a few minutes where they have significance. So what do you mean by the zeros of the Bessel function? So suppose you take j0, of x. Okay, then what you'll see is you'll see a graph that looks like this. And these are the points where the function crosses 0. So, these are what you mean by the zeros of the Bessel functions. So, these are what you call the zeros of the Bessel function. Okay. So, these points, these values of x, so these are so at the 0 of x, so jv of x0 equal to 0, then x0 is called a zero of the Bessel function, and these actually turn out to be very important in lot of applications. Okay. Now, next I want to take the Bessel functions and show how they appear very naturally when you are dealing with circular boundary problems. Okay. So what is a circular boundary problem? So you can imagine that you have something like let us say a drum. Okay, a vibrating drum, and it is basically clamped at this ends. Okay, so it's the drum is basically clamped at this ends. Okay, so it can't move here. Okay, and the drum is allowed to vibrate in between. So these points are held fixed. The boundaries have held fixed. The boundary is a circular boundary. Okay, and what it makes sense to use a r theta coordinate to describe the so if you use r and theta to describe any point on the drum, and let us say r is the radius. Okay. So with respect to the center, these coordinates. Now the wave equation for this drum has the following form. So dou square by dou t square of u is the amplitude of the wave. Okay. In general, it is a function of r, theta, and time. So it is a function of the point in space and time. Okay. This is equal to c square, and you have a gradient square of u. Okay. And u again is a function of r, theta, and t. Okay. Now now the point is, what does this gradient look like in polar coordinates? So gradient is d square by dx square plus d square by dy square. So in plane polar coordinates, okay, so this takes the form. So I'll write this in a slightly different form. I'll take the c on this side. I'll write it as d square by dt square of u of r theta t is equal to, now what I'll write here, I'll write this as so if you write this Laplacian in plane polar coordinates, so Laplacian in polar coordinates. So the Laplacian in polar coordinates has this form, d square by dr square of u, okay. I am not writing the theta phi r theta t dependence, okay, plus 1 by r dou u by dou r plus 1 by r square dou square u by dou theta square. So that is what you have on the right hand side, and the left hand side you just have d square by dt square, okay. Now let us look for solutions that are spherically symmetric, okay, or not spherically symmetric, I should say they have a circular symmetry, okay, are symmetric in theta, symmetric and independent of theta. So if you look at u that is independent of theta, okay, so you say u of r theta t, I'll write it as u of I'll write this as u of r t, okay, and further what I'll do is I'll say that I can write this as as a function only of r times a function only of t, okay. I'll write it as separately as a function of r and t. You don't need to do this, but this will just illustrate what we want to say a lot quicker. So if you do this, okay, then the second derivative, okay, so I can write this as 1 by c square, okay, and d square by dt square is just g double dot times w, okay. So I'll write w g double dot. So double dot implies g double dot equal to d square g by dt square, okay. So this will be equal to, now d square by dr square of w, that I'll write as w double prime, okay, and g plus 1 by r w prime g plus 1 by r square w, sorry, this term will not be there. So this term will not be there because w is, because your u is independent of theta, so that's all you will have, okay. And now if I divide by wg, okay, then I can get, okay, where I should mention w prime equal to dw by dr, okay, and similarly for w double prime, okay. So now what you can do is you can just divide this equation by wg, okay, and what you can write this as 1 by c square g double dot by g is equal to w double prime, and I'll just okay, so plus w prime by r divided by w, okay. So I just wrote it in this form, and what you can see is that this is only a left hand side is only a function of t, right hand side is only a function of r, okay. So that means if these two functions have to be equal, so this has to be equal to constant, and that constant, okay, you can show that it should be a negative value, okay. So I'll just take that constant as minus 1 by k square, okay. So this is a constant, so this is a negative constant, okay, and this is just a choice, we just call it minus 1 by k square, okay. So then what you can write, so now I am interested mainly in the differential equation for w. So I can write a differential equation for w that has the form r square w double prime plus r w prime plus, so I multiply by r square, so I'll get r square by k square w equal to 0. Okay. And if I just make a substitution, I want it as minus k square, not minus 1 by k square. So, minus k square. Okay. So, I will take it in this form and then I will get, so I will leave it as minus 1 by k square. Okay. And what I will get is r square divided by k square here. Okay. So, that is, we will just leave it in this form and then we will work it out. Okay. So, immediately you can see here that this looks like the Bessel equation. There is a k square floating here. Okay. So, what we will do is we will just take this, we will just multiply out by k square. Okay. So, you will get k square r square w double prime plus k r rather k square r w prime plus and I will get r square w equal to 0. Okay. And why I did this is, suppose I make a change of variables, let us say I say s equal to k r. Okay. Then I can see that dw by ds, or rather dw by ds, this is an ordinary differential equation. So, dw by ds is equal to k is I'll write it as is equal to dw by dr into dr by ds is equal to dw by dr into, now dr by ds, okay, dr by ds is 1 by k, and then similarly for the second derivative. So, similarly I can write d square w by ds square is equal to 1 by k square d square w by dr square. Okay. So, dw by dr I wrote as w prime. Okay. And you can see this, you can see where we are going. Okay. So, when you do this, okay, you rearrange everything, you will get an equation that looks like s square d square w by ds square. Okay. So, you substitute this and then do some cancellations and you will end up with a very nice looking equation plus s dw by ds. Okay. And you will get a term that looks like plus s square w equal to 0. And this is nothing but Bessel equation with v equal to 0. Okay. So, what is the solution of this equation? So, that means the solution, okay, at least one solution. So, one solution is J0 of S, okay, or equivalently it is J0 of KR. Okay. Now, J0 of KR, okay, so this is a solution, and this is a solution to this, it appears naturally in this circular boundary problems, and you can see that all that we had was s square w d square w by ds square and s dw by ds, okay, and this third term, and you can see that even if we had started with a problem that had a theta dependence, okay, this would just, you would just get an additional term, but still you would still be able to express it in terms of Bessel functions. Okay. So, the Bessel functions appear very naturally, okay, and interestingly the boundary condition will be basically at r equal to r, okay, we should have u equal to 0. Okay. So, that means I can write that J0 of K r equal to 0, that implies that K r is a 0 of the Bessel function. Okay. So, again what I said is that you have the 0 of the Bessel function appear naturally. Okay. So, if you think of what the solutions look like, so if you imagine, if you go back to your drum that you had, Okay, if you imagine this to be your this, I will show it in green. Okay, so if this point you have r equal to 0 and you imagine that you have these Bessel functions, okay, and they should go to 0. So, right at r equal to 0 it should coincide with a 0. Okay, and so this is what it will look like in one direction, but it will look the same way in all directions. So, basically you will have these waves that have a large amplitude in the middle, okay, then they have low amplitude here, and then another part with a large amplitude. So, you might get something that looks like waves that look something like this, which have a large amplitude here in the middle. Okay, and this is exactly what so it will look from the side view, it will look something like this. Okay, so this is what your oscillations, the vibrations of any drum that you take will have these Bessel functions. Okay, so I just wanted to show you where Bessel functions appear very naturally in circular boundary problems. Similarly, if you take a particle on in a circular region, restricted to a circular region, you will again see the Bessel equation appearing. Okay, so I will stop here. So, in the next class I will talk about Laguerre polynomials and how they appear in solution of the hydrogen atom problem. Thank you.